together with you. Also here we will use the same function as before, this force function with this super strange quantifier structure. And the algorithm starts like before and like usual. We start by saying that our first guess or version of what the winning region could be is simply our set of force safe states. Next, I will start an endless loop, which is hopefully not really endless. And the first step we do here is we ask a QBF solver. Let me write it like this: QBF sat, which means we ask a QBF solver whether the following formula is satisfiable. Namely, what we would like to get is a state which satisfies this formula W, which means that is part of our winning region, and at the same time this state should be part of force E of not W. So what this question basically asks is there a state in the winning region for which the evil environment can make sure that we reach a state outside of the winning region next? So illustrated graphically, like here, we have here our set of all states. This is our current version of the winning region, which is initially just P. Now this question to the QBF solver asks whether there exists some state, let's call it S, for which the evil environment can enforce to reach a state which is outside of our winning region. Actually, this, what I wrote here, is of course not really in this premix conjunctive normal form, so we cannot directly ask this question to the QBF solver, but we can easily write this down. What we really would like to know is whether there exists a state X and some input which can be chosen by the evil environment, such that no matter what the good system does with the outputs, we will come to a next state X prime. This state X prime is, so the original state X needs to satisfy the formula W, which basically means that the state we are seeking is inside of this W region. And by taking one step of the transition relation, which is the formula over xi o and x prime, we end up in a state which is outside of the winning region. So this x prime, which is computed by the transition relation, is actually outside of the winning region. This is how the formula would look like in its full beauty, and this formula we can directly pass to the QBF solver. And what the QBF solver will do is it will give us two parts of an answer. I write it like this. So let's say we have such a variable sat, and the QBF solver sets this variable to true if this formula here is satisfiable, and to false if this formula is not satisfiable. And in S, this QBF solver returns us the satisfying assignment for the x variables, which is basically just this, exactly this bad state, which is in the winning region, but the evil environment, let me draw it like this, can enforce that we leave this winning region. Now, of course, there are two things that can happen. This formula can either be satisfiable or not satisfiable. Let's start with the easy one. If this formula is not satisfiable, so our QBF solver sets this variable sat to false, what does this mean? Any ideas? Yes?
This is already the winning region.
Exactly. Because there is no way for the evil environment to find some state and input such that we leave the winning region. So we are already done. We already have found our correct winning region stored in the variable w. So all we have to do is, let's say we return w as the final result. Good. What if this formula is actually satisfiable? Then this subvariable will be set to true and we will get such a state S. And this state S we will get, as already mentioned before, as a so-called cube. So S will be something like this, not x1 and x2 and not x3 and x4 and x5. Which basically just means x1 is false, x2 is true, x3 is false, x4 is true, x5 is true. So this is a satisfying assignment, concrete values for all our state variables, which makes this formula true. And this cube represents exactly this one state in our state space. So we now have this bad state S as such a cube. What should we do with it? Yes?
Exclude from the winning region.
Perfect idea. Let's do this. How can we do this actually? So somehow we need to refine our formula. Say the new version of the winning region is the old version of the winning region and not S. We can directly say S. S is just a formula which evaluates to true whenever we have exactly this state at hand. And by saying the new winning region is the old winning region and not this formula, we exclude exactly this one state from the winning region. Actually, this algorithm already works. Let it run and it will iterate over all problematic states in our winning region and exclude one after the other. Actually, there is one small thing missing. When we exclude a state from the winning region, we can also check whether this state which we include is one of the initial states, because if we exclude one of the initial states, then this means that from the initial state the evil environment has a strategy to enforce that we violate our specification. So this means basically that the specification is unrealizable. This check we can add simply by saying if, how do I write it? We could say S satisfies I, which is a formula of the state variables. Then we know that the specification is unrealizable, so we can stop. And just, let's say, we return unrealizable. Good. So this algorithm would work. Unfortunately, it is not very clever, because what this algorithm basically just does is, for each and every state which needs to be excluded from the winning region, it will find it and exclude it. And there can be millions of such states. We already faced the same problem when we discussed these learning algorithms for relation determinization. There we discussed a very simple trick to make this algorithm scale better. I will just write it like this. Before we actually exclude this state S from our winning region, we will generalize it into a larger region of states that can be excluded in one step. So instead of just excluding this one state here, we will try to enlarge it into a larger region and then exclude all of this region in one go. How can we do this? Well, there are plenty of possibilities how we can do this, but one very simple way to do this is the following observation. Let's say we have exactly 5 state variables, x1 to x5. Then, if we assign one concrete value to all these state variables, then this represents exactly one state in our state space. But if I just drop one of these conjuncts from my formula, let's say I just remove this one and just write the formula x2 and not x3 and x4 and x5, then this represents exactly two states. Namely, the state with x1 is true and the state with x1 is false. If I remove one more variable, let's remove another one, let's remove this one, I don't know, then we get a formula which represents four states. If we remove even one more, we get the formula which represents 8 states and so on. So the more variables we remove from this satisfying assignment, the larger is the region of states that is represented by this incomplete cube now. Now, of course, we cannot just remove all the variables or as much as possible. We have to be careful when removing these variables. What we need to ensure is that the following implication must hold. S must still imply force E of not W. This means that every state that satisfies our formula S, there can be many, many states that are represented by this incomplete formula. Every state which satisfies this formula must also satisfy this formula, which means that every state which is in this region that we are going to exclude must also be in force E, which basically means that this region contains only states that really must be excluded from our winning region, and no states that must not be excluded from our winning region. So this is a very simple trick how we can make our algorithm here more efficient. We just take the satisfying assignment we get from our solver originally, and then we start to remove variables from these satisfying assignments. The more the better. But each time we remove a variable, we check whether this implication still holds. If it does not hold anymore, then we undo the removing of this variable. Yep?
Are there any clever techniques in which order one should try to remove the
Good question.
It can make quite a difference, I think.
Yes, definitely. So actually we've tried several versions of this algorithm, and we also have versions which compute not just one generalization by dropping some variables, but all generalizations. This you can do with a very complicated algorithm. So you can compute every minimal subset of these variables such that this implication still holds. This actually led to performance improvements for certain benchmarks. The reason is that in practice, this QBF solver call is really, really expensive, but this check whether we can remove a literal is very cheap. Because, I don't know why actually, because this formula contains the negation of the winning region probably, which is very difficult to represent in CNF, I don't know really. But based on this observation that these checks are very, very cheap and this is very expensive, we just tried to compute several possible generalizations or all possible generalizations and then exclude basically not just one such region. So how this would look like is we have our state here, we compute one generalization which looks like this by dropping certain variables, and we compute another generalization which looks like this by dropping other variables.
Also, you don't just drop the largest, but all of them?
All of them,
Okay.
or just the largest, as we wish. So we can play around with multiple heuristics here. But in our implementation we just remove all of them, because the more we remove, the faster we remove things, the faster we will get to an end, basically, was the basic thought behind this. Okay. So this is the basic idea of this learning-based approach for computing the winning region. Let's return to the slides. Basically, here you have the same algorithm, maybe just with nicer animations. So just to repeat this once more, how the algorithm, the basic algorithm without this generalization works is it computes a state for which the evil environment can enforce to leave this winning region, then it excludes it, computes the next state, excludes it, computes the next one, and so on, until no more states are left that need to be excluded from the winning region. But this can be very, very tedious because there can be millions of such states. So the beta version with this generalization in the algorithm works like this. It also computes a state, then it tries to generalize it by dropping more and more and more literals, and only if it cannot drop any more variables from the satisfying assignment, it excludes this entire region in one go. And then it continues with the next state and so on. And yeah, this just explains how this generalization here drops variables, and the more variables we drop, the larger is the region of states that is represented by this incomplete assignment. And you can drop variables as long as this implication here is still satisfied, because this means that every state that is in this region represented by this incomplete assignment still needs to be excluded from the winning region. So we better do it now instead of doing it later. That's it. Let's now briefly discuss the most important differences to the previous algorithms we discussed. So compared to this QBF-based implementation of the standard algorithm, this algorithm has the advantage that it solves much simpler formulas, because all it does is it always solves basically the same formula, namely this one here. Probably you cannot read it, but let me try this trick. No. Yes. It always solves the same formula. It always contains, this formula always contains just one copy of this transition relation. The previous approach had a growing number of these copies of the transition relation, and the previous approach also had a growing quantifier prefix. Here the quantifier prefix is fixed. The only thing that grows here is W. W gets more and more complicated the more we refine and update it. But this is usually not so dramatic as additional copies of this transition relation and additional quantifiers. So this is a plus. Plus, yeah.
Does both W formulas grow, or only
yes. This is actually a little bit of a disadvantage. So in the beginning I already said that a QBF solver can only take a formula where the body of the formula is in conjunctive normal form. So it must be a conjunction of clauses. In principle, every formula can be transformed into conjunctive normal form. There are transformations like this Zetin encoding and other transformations which take an arbitrary formula and transform it into CNF. Let's say we do this once for our transition relation T. Then we can reuse this CNF in each and every iteration. The nice thing about W here is actually the following. Let's say, so in the first iteration, W is just set to P. Let's say we also encode P into CNF, then we have originally W in CNF. Now, the only update to W happens here, and here we say the old W is the new W is the old W, and not a cube. And not a cube is always a clause, interestingly. Because this S looks like this, it's x1 and not x7 and not x12, because we have already removed a lot of variables. Now, when we negate this, we get not x1 or x7 or x12. And this is actually a clause. And when we have CNF and make a conjunction with a clause, then this is a very simple operation. Because basically a CNF is just a set of clauses, and we just need to add this additional clause to our set of clauses. Because this W is already a conjunction of such terms, and we just add one more. So this is a very simple update basically, and this means that this will always be in CNF. This we also have in CNF because we transformed it initially into CNF once. Now, a conjunction of CNFs is also a very simple operation, because a CNF is just a conjunction of some things, and the conjunction of two CNFs is just joining all the clauses together. So this is also a very simple operation. Also this and is a simple operation. The problem is actually this here. We need to have the negation of the formula W. If W is in CNF, then building the negation is kind of complicated. The straightforward way to do this is we just introduce one additional variable that represents that a certain clause in the CNF is force, and then we have one huge clause which represents that one of the clauses of the original CNF must be force. Not so important, but the message is that this operation is actually quite expensive. I mean, you can compute this very, very fast, but it makes the formula large, because for this negation you have to introduce a lot of additional clauses and additional variables. Yes, and now I completely forgot what you asked initially, but I'm sure this answered your question.
Yes. Thanks.
Okay. So what were we talking about actually? We were talking about the advantages to the previous approach, and we said that the formulas that need to be solved are simpler, which we just discussed. Because for the previous approach we had this growing quantifier prefix, and we also had the growing formulas with more and more copies of these transition relations, which can also be very complicated. Yes. Another advantage, we will talk about this a bit later, is that this algorithm can also actually easily be parallelized. The most important disadvantage here is that this approach probably requires much more calls to the QPF solver than the previous one. Because, yeah, I don't know, because we may not be able to exclude a particularly large region of states from the winning region in one iteration, so we may have to iterate over this algorithm many times. So we may have an awful lot of calls to the QPF solver, but the good thing is that all these calls to the QPF solver are rather simple. So these are the advantages and disadvantages compared to implementing this standard algorithm in the naive way. I just mentioned that this algorithm can also be parallelized. Let's talk briefly about this. So remember how this algorithm works. It computes a problematic state, generalizes it,